Hello, this is Jeremy, and in this video I'm going to show you applications of the central limit theorem, specifically the central limit theorem for means. Now, the central limit theorem for means tells me that as long as I have a big enough sample size, which we'll say is about n bigger than 30, we'll just call it, that's usually a good number. So as long as I have, we'll say n bigger than 30, big enough sample size, then if I look at the distribution of all the possible samples of that size, their particular means, then that distribution should be approximately normal. Now, how normal it will be depends on what the original distribution looked like, and if we really need to cut it off at 30 or something lower will depend, but often this occurs at 30. So again, when I look at problems associated with this, I always ask myself about the sample size first. So in this first example of an application, we're going to look at something where all the real life stuff's taken out, and we can just look at the math itself. So it says we have a sample size n equals 75, okay. First thing I note is that's bigger than 30, so it's a big enough sample size that the central limit theorem should apply. Okay. What's the probability our sample has a mean? Now, normally when we deal with probabilities, we don't talk about samples, right? We talk about individual values. What's the probability our sample has a mean larger than 221? So we're asking probability our sample mean is bigger than 221 if the mean of the original population is 220 and standard deviation is 3.9. Now we're asking about the sample mean. So typically what I do with this is I'd either use a z-table, I would convert to a z-score, use a z-table to get the probability, or I'd use normal CDF on the calculator. The problem is we're talking about x bar, not an individual value. So that means that we got to use the central limit theorem, but the central limit theorem says x bar should be approximately normal, but the mean and the standard deviation might be different. Now, it says the mean of all the x bars stays the same. So we can actually use the 220. But the standard deviation of the x bars, which is also called the standard error, will not be equal to 3.9. In fact, it will be much smaller than this. It will be 3.9 divided by the square root of 75, which I'm just going to leave like this. So that means if I want to find this probability, that what I need to do is use this normal distribution and not a normal distribution with 220, 3.9. Okay, now I can use a normal CDF because I know that it's normal. And since we're going from 221 up, we go 221. And remember, we need a right-hand endpoint out to E99. Then the next value is the mean. We're using the distribution of x bar as the sampling distribution, since this is x bar. So this is up to 220 for the mean. And then the standard error, which is the standard deviation of x bars, which you'll type in your calculator just like this, 3.9 over the square root of 75. So remember, normal CDF is found under second and VARS. That takes you in the distribution menu. You don't want to use normal PDF. That's an estimate. We just want to use CDF. And so CDF will find the area of this region under the curve, and area, probability, and percentage are the same thing. So once I do this, I end up with 0.0132. Okay, so about 1% of means will be above 221 if the population mean is 220. So if you think about this, that means we could take a random sample of size 75, and the chances are we're probably going to be pretty close to our sample mean being 220. Sometimes, though, as we can see here, about 1% of the time, it will be bigger than 221, which is much further than you might think a sample mean would be. What we're seeing here is the sample error. So sample error is something we can actually measure. Now, let's say you don't like using normal CDF, you like using a z-table. The thing is, your typical z-score, let's say you wanted to do it that way, your typical z-score, which is x minus the mean divided by the standard deviation, well, it's a little bit different when you're talking about x bar, because now the point you're interested in is actually x bar. The population mean is that mean of means, which happens to equal the population mean anyway. And then this becomes the standard error. So I'm actually talking about x bar stuff now. And so the standard error would be sigma over the square root of n. So you'd have to calculate this particular z-score. And so if you calculate this here, we're curious about 221. And we're subtracting a mean of 220 and dividing by the standard error, which is 3.9 over the square root of 75. And you calculate this, you get a z-score of 2.22. Okay, so we already found our answer this way, but if we wanted to use the table, what we would do is look up the area to the right, since we're greater than 2.22. And so what we're actually finding is that this is equal to this probability. And so if you look this up on a table, once again, you should get approximately 0.0132. Since it's area to the right on the table, you only have area to the left, so you'll have to subtract 1, but this will be your final answer. So if you use the table, your z-score is a little bit different. And if you use normal CDF, the main thing you have to change to is essentially the same thing that changes in the z-score, and that's your standard error. Now notice here, I have a big note. It's in bold, so it must be important. It says no hint as to the shape of the population. We have no idea what the original population looks like here. All we know is that we have a large sample size and you're talking about the sample mean. So if I was to ask you a question about an individual value from this population, you couldn't answer it. So before I asked about a value from a sample, right? I said we take a sample, what's probably the sample mean will look like this. But if I just said, what's the probability of particular X from this population, so probably X bigger than 221, then I can't actually answer this. Not because we don't have the ability to, but simply because there is no answer. Unless I know this population distribution, I can't answer questions about X. I can only answer questions about X bar. The central limit theorem gives me the power to answer questions about X bar even when we don't know the distribution. But X's come from a distribution, whether that's binomial, normal, whatever it might be, and I have to know that distribution to find the probability. So here, I would have to know the distribution to be able to find information about an individual value. So as we work problems, it's important to pay attention to can we answer the question or not, and if we do, are we using a sampling distribution or the original distribution? So that comes up in the next couple of examples. Okay, so notice the change here. Now we're talking about a real application. I say the mean height of women in the US is 64 inches with a standard deviation of 2.75 inches. And the distribution of all heights is normal. Now, the first thing I think about here, distribution of all heights is normal, is that's the population. So in other words, this population is normal with a mean of 64 and a standard deviation of 2.75. Okay, we take a random sample of 40 women from this population. The first question asks us, what's probably the sample mean? So of those 40 women, if we take an average of their heights, what's the probability that's less than 62? So that's asking about an X bar. The reason I know it's asking about an X bar is because of this phrase right here, that is X bar. Since we're asking about X bar, I have to know if the central limit theorem applies or not. So I say, well, what was our sample size? It was 40. So n's bigger than 30, so we can apply the central limit theorem. That means X bar is normal, or at least approximately, with a mean that's the same as our original, so 64, but now remember we have a different standard deviation, that's standard error. So it's equal to sigma over the square root of n, which is equal to 2.75 divided by the square root of 40. Okay, so again, that's the central limit theorem because we have a big enough sample size. It doesn't matter the original population was normal, except for I could actually have a smaller sample size in this case. But here, I could just check the sample size because it was already big enough. If n was smaller than 30, I'd go back and say, was the population normal or not? Because if the original population is normal, and you have a small sample size, your sample should still, or your sample mean, the sampling distribution should still follow a normal distribution. Well, now I have to decide if I'm going to use a z-table or normal CDF. So the z-table is illustrated in the textbook, so I will use normal CDF, which finds the same information. And so since we're going to the left, I need a left-hand cutoff, so this is minus E99 up to 62, and then our mean. And again, because we're talking about X bar, I got to use the standard error, so 2.75 over the square root of 40. Okay, so calculating this on the calculator, again, that's second and VARS, I get a very tiny probability, 2.12 times 10 to the minus 6. So why is it so small? Well, 62 inches is 2 inches from 64, right? And you may say, well, that's within a standard deviation. But you forget that we're not looking at the population distribution anymore. We're looking at the sampling distribution, the distribution of sample means. The standard deviation for that is much smaller. So in other words, it's much more, it would be much more typical or possible to see a woman who's very tall or very short, an individual person, because of individual randomness. But it would be very strange to have a group of 40 women such that the average height was very tall or very short, especially if it's a random sample. So as you get samples, everything should be coming closer to the mean when you deal with sample means, and that's what this is reflecting. Now in part B, it says what's the probability an individual woman is taller than 60 inches. Now, we're talking about individual now. So this is an X from this population. Taller than 60 inches. So when I deal with X, just an individual value, I look back up here and I say, do I know information about the population? I do. Heights are normal. So X is normal. We know this time. And we have up there that the mean is 64 and the standard deviation is 2.75. That means that I can use normal CDF or the normal table to find its probability. So in this case, this would be normal CDF of 60 up to E99 for a right-hand cutoff. The mean is 64. And the standard deviation this time, because I'm talking about individual value, I use this. Standard error only goes with the sample mean. And this time I get a probability of 0.9271. So in other words, it's very likely that we'd see an individual person taller than 5 feet. But if you were to look at perhaps the sample being like this, you might get a different answer. And so that's all about the sample distribution versus the population. So in the previous part, I couldn't answer a question like this because we didn't have information about the original population. But this time I could. So again, the central limit theorem helps us with questions about X bar, but we have to pay careful attention to, are we asking questions about X bar or not? So I think it's worth going through one more example, and I think you'll really see the key here. So this time we're told the length of phone calls made by cell phones in a certain country follows a skewed right distribution with a mean of 8 minutes, standard deviation of 2 minutes. Now, skewed right could mean a lot of things. I mean, it's a general shape, right? So it's like this. So it means most calls are pretty short, but there's a tail out towards longer and longer calls. Now, skewed right, though, this is also skewed right with a very short, shallow tail. There's all kinds of shapes that would fit skewed right. And so I got to be careful while we have this information about skewed right, it's not specific like normal or binomial or Poisson or any of these other distributions we have. So all we really know is mean is 8, standard deviation is 2, but we don't know much else about the population except for a general idea of skewed right. So for part A, when it asks me about a single phone call, we don't have enough information to answer this. So when you ask about a single phone call, you're asking about the population. And that population is skewed right, but there's many skewed right distributions. And so I don't have enough information about the population to answer this question. If I knew it was normal or something like that, then I could answer the question like we did before. But then when it comes to something like this, what's probability that in a sample of 45 phone calls, the mean, so you're asking about X bar, is less than 8.5, I can answer. Because the central limit theorem says no matter what the original distribution, the distribution of sample means will be normal as long as you have a big enough sample size. And this time we do. 45, central limit theorem applies. And so the mean will be the population mean 8 and the standard deviation. In other words, the standard error, because we're talking about X bar, would be the standard deviation of the population over the square root of your sample size. So my answer here, I can actually answer, use either the table or normal CDF and say, okay, it's going to be the area under the curve below 8.5. So it'll be minus E99 up to 8.5. And then our mean is 8 and our standard error, 2 over the square root of 45, which you can type in the calculator just as it is. So this one I won't go through the calculator work again. I'll just tell you, you should get 0.9532. You should double check that you get the same thing on the calculator, or if you're using the table, that you get the same thing on the table. Just remember, if you use a z-score here, you're going to have to use the standard error in that z-score. So all of our applications of the central limit theorem for means will look like this. And so the biggest thing when you're working on these types of problems is pay attention to sample sizes. Ask yourself if you know about the original distribution. And the biggest one, are you trying to find the probability of a sample mean or an individual value? Because the first two questions basically are based on this last one. Are you finding the probability of an X or an X bar?